probably we can start the session 7 on today from 8:30 to 10:30. Then thereafter, we'll be having a 15 minutes break. Then 10:45 to 12:45, we can go ahead with the session 8. So can somebody confirm my audibility? Can you hear me?
Yes, sir.
All right, that's fine then. Okay, so basically we already have covered 6 sessions and hope you received your first assignment and you are working on this. I provided, I think, 3 weeks for submissions. Please go ahead and complete that without requesting extensions at the last minute. I know everybody has busy schedules and probably will be usually procrastinating, and it's better if you can attend those assignment questions and work on that. Better to go ahead and search further, and I already provided reference books and for further reading, another direct more books included in each section. Probably can go through the relevant sections and get deep understanding. Definitely, though, the first assignment will help you on your final examination as well. Additionally, you are getting 40% from your assignment, 60% from your this thing, the final examination. Usually, the first 6 sessions covering almost roughly about 40% of your final examination questions as well. So it's important to focus on the first 6 sections if you want to score majority of marks beyond your expectation. So that's quite important because that is the area we have covered almost all the fundamentals, troubleshooting fundamentals, theories, and all those things come on to every section in this coverage of the course. But from today onwards, we'll be moving more from session 7 onwards. We are moving ahead with the industrial best practices and industrial applications and how we are doing networking in industries, and most of the topic are somewhat latest or the not traditional as we covered on some of the traditional topics on the MC4004 course, which is on the first semester. I need some of them to some of them to recap as reminders to you in case of explaining some of the topics today. Probably we can start the session on with the fresh mind in terms of these are the next lectures are new, somewhat new in terms of context. Maybe the coverage of those topics and areas somewhat new to you, but it's important therefore it's important to join and attend the sessions frequently because these are somewhat required in deep understanding to answer questions on the final examination, which is essay, which are included essay type questions. So are there any questions on last 6 sessions or any on your assignment questions? Probably we can discuss before I start this. All right. So for the session 7, we are starting with the discussion on the different traffic transmission types, which is unicast, broadcast, and multicast. And we need to get a clear understanding between unicast, broadcast, and multicast. And we are going a bit deeper on IP multicast fundamentals today. Then we are starting the IP multicast troubleshooting and the IP multicast security implementations. Since your course mostly related to security. We are covering how to implement IP multicast security as well. So this is the coverage on the first coverage on the session 7. Mostly, first we can discuss on the unicast, broadcast plus multicast differences. I'll be using some of your session 1 network design course topics as a support for there, and then in there we can do something called bump traffic. I will explain you that what's B, U, and M means. And then we can start IP multicast fundamentals, because this has not covered before in the network design. It is mainly targeting multicast troubleshooting, especially somewhat contrasting to unicast and broadcasting. And first, I will explain why IP multicast, then multicast history and fundamentals with the standards and the publications. And there are two major types of IP multicast, the areas of multicast: layer 2 multicast, layer 3 multicast, which is based on the OSI model, layer 2 and layer 3. So before moving that, let me recap on or summarize on some of the areas what we have covered. From session 1, we had an introduction, the network lifecycle, and we went into the definition of all the areas. Then session 2, uh, we were on network troubleshooting approaches and troubleshooting fundamentals. On the second day, we covered fundamentals of network risk management. Hope you can recall this. All this covered in your first assignment as well. We discussed on the three types of exposures. Hope you remember fragileness, robustness, anti-fragility. And then on the third session, we had a discussion on network complexity and network failures by different planes: control plane, data plane, and management plane. Then we separately discussed on the software and hardware failures of network components. Then this is it. And discuss somewhat on the centralized controller functioning, and which is software-defined networking and the protocols related to that. And network function virtualization, which is transferring network functionality from this particular hardware devices to software instances. And network failure calculations we made on uptime, downtime, and deeply discussed on this particular area. And then we covered on performance aspects of performance degradation and failures with the performance metrics. We discussed on 6 performance metrics, and one of them selected and discussed bit on the common test tools as well. We'll be probably will be having troubleshooting sessions based on the lab sheets I will be providing to your course coordinator or network course coordinator. Then we'll arrange troubleshooting sessions based on your availability, and so the separate instructor will be covering those troubleshooting sections. And we took one of the metric, which is latency, as a reference to explain how we can optimize these matrices by taking latency as an example, and how far we can go ahead with this. And we discussed on the end-to-end latency, from the optimization from the host networking and the up to the remote network and the intermediary network devices as well, and define the network latency with 5 components: distance, delay, serialization delay, queue delay, forwarding delay, protocol delay. And we discussed each and every subcomponent, how we can optimize further as a metric. We had a detailed discussions on different bandwidth sizes and how each Ethernet standard defined in its effective bandwidth. And we discussed details on serialization delay. By increasing the bandwidth, we can reduce the serialization delay, which is a major component in terms of latency optimization these days for data centers. And we had uh, uh, we had discussions on this Ethernet roadmap, which is started 1980s with 10 Mbps. Now we are moving up to current days. We are having 800 GB as an standard, and most probably 1.6 terabit Ethernet will be there at the end of this year. Based standardization already done, but in still 1.6 is not officially released, I guess. And we had a uh, more uh, more discussion in terms of how to reduce the latency end to end, and our expectation in the modern day, then cut through latency, uh, defined against store and forward, and explain the function of cut through switch was store and forward switch. And this is a slide how we explain on the kernel bypass to avoid the latency induced by TCP/IP stack, which has developed 50 years back, not in a mind of latency optimization. So probably rather than tuning TCP/IP stack of the kernel, probably you can entirely bypass the kernel and directly communicate with the applications through sockets at this user space of the kernel above the kernel. And some of the proprietary methods are there, like open non-load, which is from AMD, by using specialized network interface cards, which are called SmartNICs. And we discussed on the RDMA protocol, remote direct memory access, in terms of functionality of TCP offload engine, which is giving more hardware-based networking acceleration on the I/O adapter or the network interface card by offloading the network host networking functionalities from OS kernel to the network interface card by using SmartNICs. And another way of doing the additionally different buffers at the OS level will be offloaded to adapter buffers, or functionality will be adapter buffers directly communicating with the application buffer set the user space by avoiding the transmission through the operating systems and its subcomponents. So RDMA is a modern data center protocol quite used in the high performance clusters and ultra low latency networks, uh, especially the and additionally we have been discussing another functionality of based on something called von Neumann bottleneck, which is somewhat suboptimal in terms of the traditional CPU architecture. Now there are ways to avoid this, and by using something called bypass capable adapter on the SmartNICs. So that's called zero copy architecture by using kernel bypass, as we discussed before, and this with the zero copy functionality of modern SmartNICs. We can get these latency optimization by using selecting these cards and by using these protocols. Mostly RDMA protocols are based on something called InfiniBand protocol stack, which is different from the TCP/IP or Ethernet stack. And we discussed on the InfiniBand roadmap as well, and compared different latencies of different variations of between Ethernet and InfiniBand. And the software stack handled by something called entity called Open Fabrics. That's for your information. And modern networking not only depending on the entire protocol stack change, but now supporting InfiniBand stack by using on top of Ethernet as well as on top of TCP/IP, which is IP and UDP protocol supported, and the above upper layer protocol still on InfiniBand. For the modern day class data center clusters are mainly can be built for AI and machine learning, or the data analytics based on these technologies like RDMA or Converged Ethernet, which is the root is coming from the InfiniBand protocol stack, but bottom layer protocols supported with Ethernet and IP. So Rocky version 1 supported with Ethernet, and Rocky version 2 supporting Ethernet plus Internet protocol and user datagram protocol above that. Upper layer protocol still on the InfiniBand transport protocol stack. So these are some of the developments in terms of to reduce the latency. This was the example. So we took latency as an example metric to how to minimize the network for data centers and the modern networks based on the workloads such as the machine learning and AI. So these are the reference books. Then session 5 and 6 on the last week. We discuss further on scaling, aggregation, reliability, resiliency, and redundancy under the as a subtopic of network troubleshooting fundamentals. And the session 6 was based on the failure modeling. So I don't think I need to cover almost most of the things because we were in touch on the last week. Then layering and aggregation discussed especially on the access distribution and co-layers as an example. And this was not the high-level design document based on the layering and aggregation and enabling the redundancy through the ISPs and having multiple devices like routers and the firewalls, and the separation of failure domains by building a security trust boundary. And we discussed on the protocols such as the first of routing redundancy protocols such as HSRP, VRRP, and GLBP. We had a small explanation on failure domain isolation by creating VLANs and by using firewalls and DMZ zones in between inside and outside. And I took a reference as a 7-layer model for the exploration of how to separate vertically and horizontally in terms of OSI modeling. And we discussed bit on the DoD, which is the TCP/IP model with the 4 layers, and then bit of alternative models such as iterative and hybrid model due to the developments of latest technologies such as tunneling and what's called virtualization address for the network modeling. So if you are doing failure modeling, you should you can still use some of these fundamental models of networking. And then we had a detailed discussion on the spanning tree architecture, which is the layer 2 loop avoidance protocol built sometime back 1980s, I guess. So still we are using these, but modern day data centers having challenge of something called oversubscription, which is by using the spinning tree protocol to avoid the loop, it's building the virtual tree and enabling the communication only by using these tree root and branches. And most of the physical links are blocked there. It is not optimal for the data centers now, this is the expectation of data center because data centers are mostly most of the majority of traffic between the servers, which is called server to server communication. Sometimes we call as east-west traffic, and the client to server communication usually named as north-south traffic. For the east-west traffic of the data centers, we need to have something like this as the optimal behavior. So now then these new architectures evolved by still avoiding the loop, but it's quite something like this, not spanning tree, but it should be something like fat tree. So they recently the modern architectures are based on fat tree or different variants of it are there. These are non-blocking structures. We call the spine leaf architecture. The middle switches are mostly identified as spines, and which are aggregation switches, and the leaf switches are the one on the edge connecting to the servers of data center. So the modern data centers are built usually based on the spine leaf architecture rather than using spanning tree architecture, which is traditional and still good for north-south traffic, but east-west server-to-server traffic you need to be you need to consider in terms of data center building. So most of the first six sections or sessions we covered on enterprise composite enterprise campus model or enterprise campus network design and troubleshooting, and additionally some of the areas of data center networking also covered. But we are not covering is some ISP based network engineering or network troubleshooting, because that's beyond this particular course. And I included a few slides for your further reference as appendix, including the book by somebody named Radhya Perlman, who is the founder of Spanning Tree Protocol. Still, she is in life, and she developed this protocol while she was working for MIT, which is the famous technical university in USA. And as PhD thesis, she submitted this spanning tree protocol algorithm, and now quite famous because still we are using this protocol for north-south traffic on almost all the switches and the layer 2 devices in the modern day networking. And I included few slides on with the the OSI and TCP/IP models with the details in terms of for your further further understanding based on the network design and how we segmented. And you can see in this particular appendix slide, network to network layer to network layer communication usually handle as we identify those as packets. The data link layer we call packets, or the data chunks as frames. And the physical layer we call bits and bytes, or physical layer usually for the networking, we call those as bits. And between data center layer to network layer, we are mostly mentioning those as sockets for the media. And between physical layer to data link layer, there are queues to handle the traffic in terms of to avoid losses and the speed mismatches. So basically, this is a kind of identification. We can summarize what's called packet, what's called frame, and what's where the bits reside. And this is a kind of a summarization maybe you need to have in your mind for the best of troubleshooting as a troubleshooting fundamental. And I further included TCP/IP stack and its own different protocol stack. We had a bit of discussion on, I think it should be covered on your course MC4004. Just for your recap, I included this data link layer having ARP, Address Resolution Protocol, and DHCP, Dynamic Host Configuration Protocol, which is providing your IP address automatically as a lease. And ARP is to match your IP address with the MAC address of your network segment. And Internet Protocol, you know that IP address belongs in this particular layer, and TCP Transmission Control Protocol, which is the reliable protocol. It's mainly on the transport layer and some part of it on the session layer. The UDP belongs to the transport layer, which is called User Datagram Protocol. The DNS, mostly we need to discuss today on the UDP because multicast, it is possible to use UDP unreliably in the unicast traffic patterns, but multicast heavily used on the UDP, which we can discuss later. HTML is the hypertext markup language, which most of the web applications are based on HTML. And DNS is domain name service, which is mapping your MAC, your IP address to a URL or domain name. So RTP is a protocol which is real-time protocol, mostly for the reservation of traffic reservation, especially traffic path reservation, especially on the video and audio traffic, quite useful. And ARP is one of address resolution protocol, which is quite useful in terms of, probably we can discuss further in later as well when we are discussing the different traffic patterns against unicast, multicast, and broadcast. Because ARP is a heavy user of broadcast, which is kind of a mandatory protocol for every VLAN or every subnet which you are connecting. And again, this was another mapping between OSI 7 layer and TCP/IP protocols for you to map these different protocols on or with the different models and layers of it. And you can see that IC, especially this ICMP, is a protocol we are using for the ping application and trace route application, which required for the troubleshooting, and that is there on the network layer. And so other protocols, you can know that Telnet is a protocol previously used by most of the network engineers to for the network manageability and connecting to the network devices by using CLI commands or by first telnetting. So now modern day, mostly depending on the SSH rather than telnet is not secured. And file transfer protocol, you obviously know it's mainly for the file transferring applications. And DHCP is, as previously mentioned, it's IP assignment protocol, auto IP assignment protocol based on this. And TFTP is another variant of FTP. Sometimes it has been used before for the transfer of network operating system images from your machine, the servers or machines to the network devices. We are hosting TFTPs to get imported the network operating systems from the central location to network devices for their upgrades or downgrades. SMTP is a protocol quite useful in the mail communication between mail servers. SNMP is another protocol at the application layer, which is called Simple Network Management Protocol, quite useful in terms of managing networks, especially on alerting of the failures of component. For an example, network switch having couple of fans. If one fails, it will be, you can put up SNMP to notify you by MIBS management information basis by implementing with the support of SNMP protocol. And network management require this alerting and stuff of prioritizing them for you to attend. Those are some of the protocols which we can discuss based on the TCP/IP protocol stack. TCP, obviously, you know that as a transport layer protocol, and UDP is another protocol which is spanning between, which is on the transport layer specifically for the unreliable datagram protocol, which is for the without having the functionality of reliability of TCP, because it doesn't go ahead with the verification process, which we call three-way handshaking. So those are the some of the aspects. I just need to give you a recap on what you have learned on the first semester, which is useful in your troubleshooting course at this time. And again, this is another representation with this, but still I wanted to include this slide because you can see the network layer. You can see some part of ARP is there because IP address is getting involved. ARP address resolution protocol is doing MAC, IP address to MAC address mapping for your communication. The real communications happen through the MAC addresses, which are physical addresses on your network cards. And the IP addresses are virtual addresses, which you are using to route between different subnets or different network segments. So ARP is quite useful when you are communicating with the network. So I will just give me a second. Probably I can show you some of the aspect by command line. And then other protocol as similar to ICMP, which is we have been using for the ping and trace route applications. Another multicast having another protocol named IGMP, Internet Gateway Management Protocol. And this most of the layer 2 multicast filtering handled by using this IGMP protocol, which will be discuss detail on today and the upcoming weeks. All right. Any questions? Probably this is another thing I highlighted on the last week. Even though we have ample amount of protocols on different layers, but limited choices on the internet layer and the transport layer. But top and bottom layers having several choices, including you can see that link layer, which is the TCP link layer of the TCP/IP or 4-layer model. You can see that the Ethernet 3G, 4G, now 5G is there on the link layer or the physical layers. Cabling or layer 1 and layer 2 of 4SI model. This is the 4-layer model. And the DSL, which is ADSL, you are using for the communication some places in by using Sri Lanka Telecom, and 802.11 is the Wi-Fi based protocols. All these choices are there at the bottom layers, but how about the internet or the network layer? You only have one choice, which you don't have several choices. That is the internet protocol. The previously we had something called IPX, which is developed by Novel Netware. Now Novel Netware no longer in operation, and the only option or mostly the available option for common network is internet protocol. So it is quite important to learn the internet protocol behavior and how it's configured. We'll be discussing these details, some of these details on the multicast IP address ranges within multicast IP address range explanations as well. And the transport layer having another two options, but it's still limited. For the reliable communication, you can have TCP. Unreliable, then you can have UDP from the TCP/IP stack. So you can see that application layer having several choices on based on your application requirements. You can see that it is commonly called as hourglass because in the middle part of middle layers, you are having quite a limited number of choices, but ample choices on the top and bottom, which is kind of a area of bottle, the restricting the bottle or providing a bottleneck at middle layers. So then I have included another uh, slides on the quick protocol, which is a modern day protocol. Probably can check your the data protocol usage by using Sri Lanka Telecom, or I don't know whether Dialog having something like this. So one of the days I noticed that 44%, or which is the majority of my traffic, are based on quick IETF, which is the quick protocol developed by team of Google, which is against the previously 50 years back when they're developing the TCP/IP stack and the related protocols. The security was not part of the attention there, as we discussed in the case of latency as well. So, but modern day networks require security, attention of security, and they built this secure protocol based on the UDP and TCP protocol. Most of the security abstractions or stream abstractions provided with the TLS as security layer, including there. And this is quite optimized protocol rather than using raw TCP or raw UDP usage for your modern day application developments. And it's quite useful because it's provided options of optimization rather than using a traditional TCP/IP handshake, which is not latency optimized. So these are some of the protocols you need to get understanding if you are building modern networks, and rather than using raw protocols like TCP or the UDP. This is quite useful in terms of industrial developments. Uh, so probably you can go ahead and learn on the quick protocols like quick in terms of what are the development in the industrial networking. Okay, that's about the appendix included on the session 5, and session 6 we discussed on the failure modeling and identification of failure points in the network, the strategies for the mitigation and redundancies with the clustering of approaches on the networking as well as the server level. So in here, I took an example of failure modeling by using software-defined networking and with an open flow controller taking as an example, and probably can go through this flow chart as well to get how we automate with the software-defined networking to handle the failure scenarios with a reactive approach. There is something called a proactive approach as well, which will not be discussing, but just for your understanding and explanation how this is done with the SDN implemented in your modern networks. And failure domain isolation discussed in detail with the DR options or alternative DCs to avoid single point of failure on the different layers as well, based on considering the failure points of physical or the physical plant or the power inputs or the network layers or the compute devices and the applications. Those discussed with the limitation of blast radius based on the incidents. And we had a discussion on how we implement data center and data center core aggregation and the access layers, about the different protocols we are using to avoid single point of failure. And we had a discussion on by using a simple case study or a simple example how to implement the VLAN separation of failure domain by having separate networks and joining the network and creating separate VLANs for the isolation of failure domain based on can be based on something like departments. For an example, HR department having separate VLAN or separate network segment, and marketing having another one, and how to interconnect those two different network by having multiple VLANs by using a trunk port. And these this particular slide explaining different scenarios which you can interconnect the network or isolate the network by failure domains by the physically separating and virtually separating by using VLANs. And then another option of separating failure domains or the security is secure domains for your internal network and separating with the external network and having intermediary by using firewalls and without using firewalls by creating creating routers and other separate segment for the demilitarized zone, which is the intermediate security level resides for your front-end servers. And the redundancy with the load sharing, we discussed something called first of routing protocols. There are three routing protocols discussed in there. Hot standby routing protocol, which usually called HSRP, and it is a proprietary protocol by Cisco systems, and later the more industrial more open of industrial protocol developed by the industrial authorities, IETF, which is based on the standard of RFC 2338. That's the protocol more famous among most of the other vendors. Still, Cisco is also supporting this virtual router redundancy protocol, VRRP, and those are active passive protocols. These two routers, which is the default gateway, configured by using a virtual IP address. Both the routers, active router and standby router, configured with this virtual IP, and it's a representation of this virtual router in this diagram. And when you are sending default gateway traffic to the default gateway, it's initially announced or by ARP and sending to the active router. And if active router fail, standby router automatically taking over the functions by listening to the heartbeats of active router. And it's a kind of a failover method. If one active device fails, the standby device take over the functionality of default gateway. And still that is active backup way, because only active router can forward the traffic. If it is failed only, then standby router taking over the functionality. But there is a protocol for the first of redundancy with the load balancing included. This is called gateway load balancing protocol, which means GLBP, and we discussed the details there. And it is acting as an active scenario, or both the devices are forwarding, does not wait for any failures from the primary router or something like that. You can have multiple of these routers, but but still most of the time we are handling the redundancy by using couple of routers, because if you're adding more routers, then the complexity will be higher. It's based on your design. You can find out your scalability and the dual point of failure scenario. Still, you can add more than two routers. So with knowing the risk, understanding the risk of complexity. So finally, I included one slide on server redundancy as well. For data centers, we need to have server clusters to avoid single point of failure on the servers. Usually the data centers having something like database servers. As an example, those having clusters like Oracle having something called rack servers, which are interconnecting two servers and configuring those two servers as a cluster, which synchronizing both the databases on the both servers for the redundancy. That's how Oracle the rack is the protocol or methodology they are using to configure enable the clustering of the servers for the Oracle. And further, the storages of these devices can be replicated by using the the protocols related to fiber channel, which is a different kind of networking required. That's called lossless networking. So storage area network is another different topic, which we are not covering here. Those technologies can be used to create the disk clusters for the storages. Okay, the last slide on the last week, which is mainly based on the ISP redundancy. We discussed this on detail with several options, 4 options. And this again, high-level design document based on what we have learned in terms of enterprise dual ISP internet edge connectivity with the 3 different layers connecting each other and intermediary security layer implemented with the firewall HA hardware, HA high availability, the firewall implementation with the synchronizing the state tables between the firewalls. If one fail, other will take over the functionality of firewalling. State tables are not there for the switches, but it's there for routers and sometimes routers and the firewalls. That's why they need to interconnect firewalls always if you are providing the redundancy or configuring higher availability at the firewall or security layer. Okay, these were the reference books and the further reading. So let me know if you have, since I think you may have already started with the assignment 1. These 6 sessions covering all the requirements or all the questions are from first 6 sessions for the assignment 1. So we'll be starting the session 7 on today. As I initially mentioned, unicast, broadcast, and multicast transmission compared with each other, and specifically focusing on the IP multicast fundamentals today, and then we will be starting on the network IP multicast troubleshooting, which is somewhat different in terms of unicast or broadcast troubleshooting. That's why we included that IP multicast troubleshooting sections, especially the modern day data centers or modern day enterprise networks are heavy multicast users, especially on the media institutions and sometimes the telecom applications, and as well as the financial markets. Usually the market data goes through multicast transmission, which are banks using for the exchange the stock exchange communications. There are several applications of multicast, especially on the video broadcasting and the video broadcasting applications, as well as audio broadcasting applications like we are having multinational companies, usually CEOs and the top management addressing the employees with the town hall sessions or the one-to-many sessions. So it is quite useful in the large deployments of IP multicast, especially on the modern day networks. So that's why we are covering here as IP multicast troubleshooting. Before going to the troubleshooting, I'll be covering IP multicast fundamentals for your understanding. Okay. Before we start, this is the agenda for today in terms of unicast was multicast was broadcast discuss, and there is something called bump traffic, broadcast, unknown unicast, and multicast, which is identified as bump traffic. I will explain why why those definitions are important or identifications are important. Then IP multicast fundamentals will be discussed, starting with why multicast, then multicast history and fundamentals based on the standardization approach, and then layer 2 multicast, layer 3 multicast. Then after covering the fundamentals, we can go ahead with the multicast troubleshooting based on these subtopics. And IP multicast security will be discussed after the multicast troubleshooting sessions. So next this week and next week mostly covered with these topics. Okay, just give me a second. Probably we can discuss bit on the area of ARP. Okay, do you see my screen? Still loading, I guess. Do you see the command line on this? Can somebody confirm?
Yes.
All right, okay. So basically, when you log into your machine and the host or this is Windows operating system, even Windows or Linux, you can check your ARP table, address resolution protocol table by ARP minus A. You can see that the mapping between IP address and the physical address, which we call media access control address, MAC address. That's the MAC address usually assigned for your network interface cards. And you can see that there is a definition on type as well, which we call dynamic and static. This 192.168.1.1 is the I can show you. 1.1 is the my default gateway router IP address, and 192.168.1.24 is the IP address given by DHCP server configured on the same home router, or it can be a different machine for the DHCP service. And these two are quite unicast IP addresses, so it's quite normal. For an example, if you are pinging your own IP address 192.168.1.24, when you are troubleshooting, your own machine is quite good with the TCP/IP stack implementation of the operating system. You can see that the ping can be done to your own local IP address. So how to find your IP address is another question. So this is how it's done. IP config. These are simple things, but I just wanted to give you the aspect of troubleshooting based on the understanding of the protocol and the related details. So you can see if you type IP config all on a Windows machine, you can see the several network cards in there. So if there is an Ethernet adapter which is disconnected, I have not connected. There is a physical address which is called the MAC address. It's based on the Intel Ethernet adapter, which is built-in Ethernet adapter on my laptop. And there is another adapter which is called a wireless LAN local area network connector number 2, which is again another adapter, Wi-Fi adapter, which I haven't connected or configured. Another third adapter is also there. These are some of the virtual adapters to support. You can see that Microsoft Wi-Fi Direct virtual adapter, it providing MAC addresses there, but I have it is not configured or connected at the moment. There is a mobile broadband adapter for the cellular connectivity, which is again disconnected because I am not using mobile broadband connection by using a SIM card here. But this wireless LAN adapter or Wi-Fi adapter is there with all the IP address details and everything configured. So it's based on Intel dual band wireless adapter, which is based on the standard of AC We have modern standard called PE with the Wi-Fi 7. This is, I think, Wi-Fi 5 adapter. Wi-Fi have several variants from Wi-Fi 1 to now we have Wi-Fi 7, which is the latest with a higher bandwidth and longer reachability. This Wi-Fi standard is called as Wi-Fi 5. That's why it's identified as AC adapters based on the standard. The protocol address, again, this is the MAC address starting from the 28, which is based on the hexadecimal. The usually IP addresses written here by decimals, but we have hexadecimal, which means 0 to 9 are the characters or numerals there to identify for this decimal, but hexadecimal require uh, the identification from 0 to 9 with the same digits, 10 represented as A and 11 represented as B. Likewise, 16 represented as F, which is the last numeral on the hexadecimal notations. So in this case, each and every machine in the network card in the world should have identical or the specific MAC address, which is not advisable to replicate or not expected to replicate. If you have same MAC address on the same network segment, then it is difficult to communicate within that. It should be avoided for fair communication. So you need to have a unique MAC address, and that's why each and every network card with the world require large range of identification of physical addresses. Therefore, it's represented by hexadecimal with the differentiation with 1, 2, 3, 4, 5, 6, 6 separations of the hexadecimal bits. And DHCP enabled here, which means you have not manually configured your IP addresses. You are leasing the IP address from a DHCP server configured in this network segment. If any network card or the Wi-Fi connected in this network, it's automatically searching first option as the leasing the IP address from the configured DHCP server. In my case, my router configured as DHCP server and received IP address. You can see the lease obtained, lease expired. My DHCP server or the router DHCP server is configured on the router given IP address on this 18th April, and it's valid until up to the 28th April, and after the expiration, it will take another IP address on a lease basis from DHCP server. So auto configuration enabled with the DHCP, which means if you are getting IP address from DHCP, you are getting the DNS IP address as well, just 192.168.1.1 on the same router. Usually it can be a different for the enterprises. It can be a different from the router or the DHCP. DNS servers can be different, quite different to isolate the load in terms of putting everything on the same server or same device. You can see that 192.168.1.1 as the DNS server, and there is another notation above that's based on the IPv6. Currently, the most of the topics we discuss in this course and the course module are based on the IPv4, which is Internet Protocol Standard version 4. But the modern networks, there is a new version of it, but still people stick to the IP version 4. But due to the limitation of IP addresses available, we are tend to upgrading it to IPv6, but still maintaining the backward compatibility of IPv4. So IPv6 will be not discussed in detail in this particular course, but just wanted to highlight the IPv6 is available and quite useful in the current days. And you can see the IPv4 address, which is the IP address of this particular Wi-Fi adapter. And subnet mask is configured to identify the network and the host portion of IP address. And the first 3 octets, 192.168, and 1 is the network IP address. 52 is the host portion of the IP address. And this is the explanation in terms of how you explain your network adapter connectivity and all those things by using IP config. So previously, we discussed on the ARP table. ARP table, so as I mentioned before, the real communications happens through these physical addresses or MAC addresses. So my host has IP address of, as I shown you in the IP config all command. My Wi-Fi network card has the IP address of 192.168.1.24. Its default gateway is 192.168.1.1, which is the router available in my network segment. For an example, if I need to communicate another host in my home, example, another computer in this subnet or this particular network segment, IP address can be different, something like 192.168.1.25. So I can communicate without using the default gateway for the same segment, machines of the same segment IP addresses or same network IDs. But if you are communicating something beyond 192.168.1. Range network IP, you need to send those packets to the default gateway configured on the segment, network segment. That is where the routing function happens. Usually the intercommunication within the same VLAN, which is an intra-VLAN traffic, usually require mainly the MAC addresses. But if you have applications which are depending on the IP layer, so still you can communicate by using the IP addresses and MAC addresses. Still the resolution has to be done by ARP protocol. Each and every machine or the endorsed or even the routers or network devices have ARP address resolution protocol table, ARP table, which is the ARP table we are looking at. Now you can see that 192.168.1.1, which is my router address, having a physical address, or that network interface facing my segment is having this MAC address. So my own computer Wi-Fi having this MAC address. So these table populated with the MAC addresses learning from your internal network segment. For an example, this 192.168.1.1 configured on your laptop as a default gateway, but still you need to learn the MAC address of the router, because there is no intelligence for your endos to find out the MAC address of your remote devices locally or either remotely. You need to get that mapping from the ARP table. So router address what ARP does, ARP protocol usually does, is it's sending a broadcast with asking who owns this 192.168.1.1 address. Then router responding, the user having this IP address configured, responding to the ARP, another ARP message with a media access control address it's having. So then then your endos will be populating with the ARP table with the mapping of remote IP address and the MAC address. So then it can directly send the packets on the MAC layer for the communication. So because these IP addresses are virtual addresses, but MAC addresses are real addresses required for your communication. So that's the functionality of ARP protocol, and each and every machine or network device having a ARP table to map internet address with the physical address for the communication. Real communication happens at the MAC layer or the physical layer. And you can see another IP address on the same 192.168.1.255 with the physical address of everything on the hexadecimal F, right? All are populated with F character or F numeral of hexadecimal. So this is the IP address of particular subnet we are having. The subnet address is 192.168.1.0 based on the separation of network ID from separating from the host portion of the ID. But this 255 is mean last octant is all are 1, which means the broadcast address of this particular subnet, which means if you are sending a broadcast unit for the subnet, you need to send by this 192.168.1.255, which can listen all the host configured in this particular subnet or subnetwork. So the layer 2, which means layer MAC address layer, it representing the usually broadcast represented as all live. So that's how switches understand whether it is a broadcast or unicast. Usually, if switch have received with the physical address destination as all F, then that switch forwarding it to all the ports in the switch, which means flooding to all the ports in the switch other than the receiving side. It's addressing to all the host. That's called subnet broadcast. Then there are few other IP addresses. There is similar IP address with all 255. It's still the MAC address of it similar to the subnet broadcast. It is any so if you are sending broadcast to everyone, not only the subnet, whatever the machine available in the subnet, another way of sending is all sending with the 255, which means all are F in terms of hexadecimal for the physical address. So those are broadcast addresses 192.168.1.255, 255, 255, 255 is another the full broadcast address. Still for the layer 2, which means switches, usually all the broadcast, even whether it is subnet broadcast or the full broadcast, then it's all represented by F, and it's behave similarly for both if something on the all F included as the destination address, which is broadcast. And between that, there are IP addresses starting from 224, and there's something with the 2239 as well. The 224 representing the multicast addresses. You can see all the MAC address, there is a similarity starting from 01005E for the layer 2 MAC address. These are multicast IP address ranges. These are virtual IPs. You can't configure multicast IP address for physical interfaces. I will explain that further. So these 224 IP ranges auto-defined by the operating system for predefined protocols, which you will be learning what are these the protocols reserving certain IP addresses. And 239, 255, 255 is another range of IP address, which are private IP addresses. As you may have learned on your network design course, this 192.168 is a private IP address. There is another range 172.16 to 172 or 16 onwards, those particular IP address range, which is on the class B, it is again another private range. And starting from the 10 dot range, again another IP address range defined for the class A. So in this case, I have been using private IP range, which is not available on the internet, public internet, which is starting from 192.168 1 dot range for the class C IP address. So that is so similarly multicast having private IP address range which is not available on the public internet. So it is starting with the 239 similar to 192 or 10.0172 range. There is a separate private address range starting from the 239. So this is just for your understanding. You can investigate everything even in your host computer rather than these are real practical aspects rather than your learning theories. You should consider mapping when you are troubleshooting how my host or network device configured based on these concepts, and how may I troubleshoot if you are troubleshooting based on the concepts or understanding on the networking. Okay, any questions until this point before we start this discussion on the unicast, multicast versus broadcast? Okay.
No, sir.
All right, that's fine. Okay, let me share the slides back. Hope you can see the slides now. So this is you can start based on the with the fresh mind. Now we'll be only focusing between unicast, multicast, and the broadcast. So this is the clear difference between uh, the unicast and versus multicast. Just give me a second. Okay, this is it. Right. Usually, when you are sending traffic from server to receivers or end users, let's say you are sending a stream of messages or streaming from server to end host. In this particular exam, on top of the top diagram showing, you are sending 3 streams from servers. And you have intermediary network devices and 3 endos there. So you need to send, the first thing is when you are using unicast, your server need to send 3 separate unicast sessions. So traffic need to be addressed from source of server IP address to receiver as the end host, which means addressing the end host IP address, and all 3 IP addresses need to be addressed separately by 3 separate sessions. Even if you are sending the same message, likewise, let's say your CEO addressing the heads of the departments. Now the company is quite the virtually addressing this, and your CEO addressing, and the same video content will be sent as 3 streams. I didn't. And the first hop router from the server will be sending the first message, first stream message to the second router on its own path and get received by the receiver. Then other 2 will be received on a different paths, 2 different paths, Therefore, you need to address with the three destination IP addresses or MIC addresses from server to the three clients. This is not an optimal scenario. Think like your CEO addressing the entire company with the 500 users. You are now sending 500 streams. Your network will be flooded and congested. So this is the issue in terms of if you are streaming or sending same component, same messages or similar message to multiple receivers. By using unicast, you need to have identical session for each receiver and you are quite wasting your bandwidth or your network resources because you are sending the same messages, but your session number of sessions multiplied based on number of receivers. So it is not bearable for your networks, which is having limited bandwidth and limited network resources. So to resolve this issue, we need to have multicast. So multicast is something like this. You are just sending a message from server to the first hop router, and then if there are receivers downstream, it will be replicated and sending just one copy to the next router, and likewise it's not multiplicated. If there are receivers at the downstream, only sending through the that path. So your network will not be flooded. For an example, if you are CEO addressing the entire company of 500 receivers or the employees, uh, by on your the town hall meeting or CEO addressing a monthly meeting, then probably this is the multicast is the way forward rather than flooding your network by using unicast. So your server is sending one copy to the first hop router, then there are two second hop routers. Since there are downstream users there, by some kind of signaling, your router sending one copy to the one network segment, another copy to the second network segment, and likewise it's replicating just by sending one copy of the message rather than duplicating messages. It's only entire stream flow, just sending one stream of traffic rather than multiplicating likewise in the unicast. So certain applications like video streaming or the audio streaming and sometimes the media streaming, uh, and again, the market data distributions for the capital markets or stock exchanges, which is sending the same message to all the subscribers. Usually, these multicasting methods are used for these modern applications, which is mostly necessary for enterprises, data centers, as well as the ISPs modern days. So mostly we are covering the unicast aspect of traffic by using TCP or UDP. In this particular case, we will be discussing the applications which require the multicast and the ways of doing multicast, because unicast usually implemented and the best practices develop over the years, but multicast still evolving, even though it's there for many decades, but still we have certain optimization still required for the modern day applications. Okay. Uh, Then this is another slide, which is you can see the similar scenario. You have a sender or a sending server. Then if you have three receivers, you need to send three sessions from server to the first of router or sender to the first of router. If those receivers are there downstream on any of the paths connected to the first of router, it's sending sending again the first diagram, the left diagram representing the unicast. The second side need to be or the left side need to be sent with another three messages based on the destination addresses of each receiver. But if there are no receivers, server will not send the message to that particular path because it doesn't send to a destination address which is aware by the sender whom to send. So if you are, so that's the idea, that's the flow in terms of sender to receiver in terms of unicast. How about if we implement same thing by using multicast? Still, your sender needs to send message to all three receivers, but it should not replicate to multiple addresses at any point. And it's only required to received by the requested receivers, intended receivers, not to the ones who not requested, similar to the unicast they are in that particular case. So that is how we need to configure multicast based on the optimization requirements. So hope you can understand the requirement of multicast. The question, the answer, it is answering the question of why we need multicast. This is to avoid duplication of traffic, unnecessary duplication of traffic, and optimize your network bandwidth and the resources. Okay. Then we need to discuss the difference between broadcast versus multicast. So the broadcast is sending, basically flooding the entire network. If any of the switches received broadcast, what is usually do is flooding all the ports other than the received port. So that's the behavior of usually a switch or any layer 2 device. As I previously explained on the command line session, you can see that the F1, all the hexadecimal F1 or all the destination MAC address, that is that if you send a packet with all in F on the MAC address field, then switch or network devices, the layer 2 network devices programmed to flood the network, they send that particular packet to all the ports other than the receiver. That is usually identified or named as broadcast in terms of switching. So in this particular case, you can see the left side diagram on the broadcast. The sender is a server sending broadcast traffic to the first switch, and there are receivers and non-receivers, because some of the users are not necessary to they have no requirement to receive this traffic, but still, if you send a broadcast, it will be received by everybody in the network. Even though you are not interested or interested to receiving, you need to drop the traffic. Then it requires a computing power from the host to decline the traffic. Still, the form of broadcast, if you send to a switch, it will flood it to all the ports connected to the layer 2 domain there, which means usually the VLAN or the LAN. Entire traffic from sender will be sending to the switch, and it may have connected to few other switches. Still, you are flooding to not only the receivers or computers connecting to the particular switch connected the server, but it's flooding to all the other switch ports as well, and therefore flooding entire layer 2 domain. Usually this is a VLAN or any network, layer 2 network configured based on the basis of broadcast domain. Your VLAN is a broadcast domain. If any of the computers broadcasted there, it will be flooded to all the machines in the server, the machine in the network segment, which can be a VLAN or LAN. But multicast should be something like this. You can see the right side of the picture. If sender is sending to the packet, it's only should receive by the intended receivers. It should not flooded to the unintended receivers who haven't signaled the received requirement. So that is the way multicast designed by using several protocols. Those are usually control plane protocols. That's why I mentioned there are several ways of implementing multicast. That's why I mentioned the topic based on the IP multicast fundamentals. So we are discussing the fundamentals on the IP multicast, which is based on the internet protocol. But multicast switching section is still have another optimization which we can discuss as L2 multicast. So basically, we'll be mostly on the multicast routing or multicast uh, routing for the layer 3 multicast and layer 2 multicast by another protocol which I previously identified IGMP. So in a simple terms, let me a bit explain further on a different domain. If you are difference between unicast, multicast, and broadcast. Unicast is a communication, something like if I'm talking to any of you personally, then that's unicast communication because you're communicating from A to B, one computer to another computer, one person to another person. That is called unicast. It can be bidirectional or unidirectional. It's depend on that. But still, if you are talking to from one person to another person, just the communication between you two, then that's unicast. Similarly, for the computers, you are talking from one computer to another computer by using MAC address or IP addresses. You have your own unique unique IP or MAC address, and another person have his or her own unicast or unicast IP address or MAC address. That is fair enough for you to communicate by using unicast. But for the broadcast, as I mentioned, the opposite of unicast is broadcast, or it may be a bit different. If someone want to communicate with everyone, like addressing the media, sometimes you see the president addressing entire citizens of a country, then it's a kind of a broadcast because one sending message to the everybody. So whether the receivers intend to listen or not. So usually, let's say if you go up to a place like you are on a political rally at the Tumulla Junction. Now you put up a stand in there and you have a mic and speaker. If you are giving a political message or any message at the junction, you are not intended. You may have not met those people who are receiving or hearing the message or listening the message. You are still broadcasting it to everybody who can hear, right? Not intended to any particular personal with knowing each one's name or each one's ability. It's similar to that in terms of broadcast for the networks as well. If any of the computers wanted to send the message to entire the broadcast domain or the layer 2 domain or the VLAN, then it's sending with the destination address of all in F for the MAC address, IP address wise 255.255.255 with 4 octants on the 255s, or subnet MAC address. It can be 192.168.1.255 at the last. So anyway, if you are sending a broadcast, all the numerals on the hexadecimal MAC address should be all F. So that's the broadcast in terms of usual practice by taking an example of other domain as well. So, but since I'm talking to you only the people who registered for this course right now, this is a kind of multicast communication in terms of general behavior, not the traffic behavior of this thing. So I'm addressing the because you have registered for the course and the course coordinators have shared the URLs of Zoom session. So I'm claiming the host and I'm giving you a message or doing this lecture intendedly to who has registered and joined for the course today, session today. So this is a behavior, kind of a multicast behavior, because you are sending your message to intended receivers, not to everyone like broadcast. But it's not unicast because I'm not talking to you individually right now. If I'm having a session, one-to-one session with somebody else in this particular course, it should be a unicast communication behavior. But if I'm sending a message or streaming to the many people, it's who are intended to get the message, then that's the behavior of multicast. So those are the differences in terms of with the other domain examples. Similar to the computing world or the networking, the multicast is somebody sending one computer sending a message with the multicast MAC address ranges and intended receivers who need to hear that particular channel or the multicast group IP address can signal it by using a protocol which is called IGMP and receive the message. If somebody was not intended to receive the message and not send the interest to join the session or the stream, then he will not be receiving the message because he hasn't registered for the streaming. So that's the idea behind the multicast. Multicast is a kind of a restriction in between unicast and the broadcast. And still not limited, we will be learning more it's not something intermediary between unicast and broadcast. There are several ways to configure it based on your application requirements. So those types will be discussed. So this is the simplified way of giving you the idea of unicast versus multicast and the broadcasters multicast and three different traffic types or traffic patterns to get understanding what is multicast. Any questions until I recall you something from the network design course? Okay, this is an appendix I especially included you to explain a bit on the ideas probably you learned in the network design course, which is MC4004 on the first semester. Because this is quite useful for you to understand the multicasting behavior and how switches operate. Usually, if you have a couple of the most simple network in the world is if you have two hosts and interconnected by using back-to-back cable, then it's the most simplified network. This cable, probably you need a network card on the both sides. Then you can send and transmit between these two servers. Then you need the network cards to intercommunicate on the each host and the cable between them. And so if you need to scale your network beyond the two hosts, then you need to have the people build kind of a device like this. This is usually the call as a hub. So hub is to intercommunicate between more than two device. If your network have more than two devices, which can be above 3 or above, then you need to connect this central device called hub to intercommunicate. Still, you can purchase hubs for your home usage, mostly not used by the enterprises, but because hub has its own limitations. So hub is connected. So if you need a small network, you can connect to a hub and communicate in between. But so hub has its own limitation, even though its physical topology is something like star topology, it is connecting to a centralized device. Hub internally logically works like a shared bus, which means shared bus have connection with each and every host connected to the switch. And this you can this by connecting this, only two servers or two machines can be communicate in a single time or single instance. If any other computer while communicating the two hosts try to communicate, there will be collision on the centralized shared bus. Then the simultaneous communication is not possible by using hub. So there can be collisions, and you need to address the collision avoidance mechanism, and all those things are there. Hub, it is not quite scalable when you have many number of servers interconnect to the switch because due to the collisions. And there is another issue on the hub. For an example, let's say this is a central hub. If you send the message from node 1 to intended node 3 with addressing the destination MAC address, hub is flooding all the other host as well, because it doesn't have a mechanism to filter the nodes by using a mechanism which is specified, your packet specified to a specific MAC address. A hub doesn't have a mechanism to filter the MAC addresses or any physical addresses. It's sending to everybody connected to hub other than the receiving port. So all the ports are flooded. Then once it received by the intended receiver, in this case node number 3, it will accept. All other hosts need to be rejected. It is quite unoptimized method, because all the hosts need to be dropped, what is not intended always, and it will be using computing power from all the devices and the network cards. So this is a lapse of the hub connecting. So people has developed, and there is another, the previous issue is there in terms of you can't communicate simultaneously more than two computers, because it's generating the collisions at the bus, shared bus. So now the people then, alternative to the hub, people wanted to have simultaneous communication and avoid the flooding behavior of the hub. Now there is something called the switches invented to address those two issues. Now you can if you have multiple computers, you can intercommunicate simultaneously between more than two different hosts. In this case, the host A and B communicating, and C and E communicating simultaneously without any collisions like in the bus structure of the hub. So switches usually, and it's not flooding as well. Switches usually handle this by creating MAC address table. Let's say switch has having 4 ports, port 1, 2, 3, and 4. 4 servers are connecting A, B, C, and D. What switch does is usually it has own control plane. It's building a MAC address table gradually, and it's refreshing dynamically as well. Let's say A sending a message to targeting C, and it's sending from MAC address, it's a MAC address ending with 1 and MAC address ending with 2 here, as described in this diagram. And what initially, without the one switch freshly started, it will be flooding everyone. If one A sending a message to a C, because it doesn't have a MAC address table build, dynamic MAC address table build initially, it will be flooding at the initial stage. But once MAC address table build, because first time A will be sending a message to C, and it will be flooded. On the second time, it has the entity, the MAC address table filled, because the switch learning from the source MAC address. Because if A sending a message to C, it is having source MAC address, so it's coming from the port address, switch port address 1. Now it has a mapping between MAC address of A and the port address. So switch learning that this particular MAC address is on this particular physical port number. So likewise, it's building a MAC address table. Once it builds the MAC address table for all the host by learning from the first sign. So next time onwards, for the back communication between A and C happen in this way. It's sending, because it's just checking once it's received a destination packet with a destination MAC address, checking which is connected port from the MAC address table and just sending the message to that port only. So that's how switch has optimized against the hub by using something called MAC address table. So this is the way switches are operating. This is an example of modern day switches. We will be discussing the details in this particular switch is 192 nanosecond between port to port latency. This is kind of ultra low latency switch for the data center network based on Cisco's from Cisco systems Nexus series. And switches have optimized with the several features, not only the MAC address table. You can see that time stamping and all those things are there. So just wanted to give you an idea of there are several vendors, Cisco, Arista, Mellanox, now NVIDIA, and switch vendors are there. This is just for a recap on what we have learned on the network design course, the functionality of the switch. And then the default gateway. Default gateway, if you configure your network manually or either by DHCP server, the setting should be something like this on the Microsoft. So you have 192.168.1.5, like in my case, it was 24 for the host address. In this case, the network address is 192.168.1. It is identified that by using a subnet mask separation, the host portion is 5. So host address of this particular configuration or particular PC is 192.168.1.5. And default gateway is the one who are, if you are sending any message, something other than your own IP or network IP, which is 192.168.1, you're sending any other network address, any other subnet, then it should first send to the default gateway. That's why we are configuring a default gateway. If you haven't configured a default gateway IP address for your own machine, then you can only communicate within your own subnet computers only. You can't connect with the internet. You can't connect with any other department IP networks. So it's only within your own department or only in L or on subnet configured on possible without default gateway. So if you are sending message to anything other than 192.168.1.1 range local IP address range, then it should send via a default gateway. That's why you need to configure default gateway IP address. That is mainly a router. If you are sending something within your switch network, you don't need default gateway. If you are sending something beyond your own subnet or switch network, then you need to send it to a router. The routing function implemented on this default gateway to communicate with other subnets. So usually a default gateway is a router, right? So you can configure DNS IP addresses for domain name service resolutions, which are URL to IP address. It is beyond this discussion. So basically, default gateway is your router on your network if you are sending traffic from your own LAN to remote LAN. So this is another example of it. You have 3 hosts and connected 3 hosts with the switch, and switch connecting to the default gateway router. And if you are communicating with the remote network, your devices need to send traffic first to the switch, which is layer 2 device. Then it will forward to the default gateway. Default gateway will forward to the remote network based on the routing entries there on the router. Another example. So the 2 networks are there separated by router. This is the first network having 2 workstations. You can see the 2 IP addresses there, 192.168.1.1, workstation 1, the subnet mask 255.255.255. the second workstation having another IP address, which is 1.2, and two different machines have two different MAC addresses. And then those can be intercommunicated by using the switch. You don't have to go through the default gateway or the router. And router connected with, it's one of the interfaces connected to the network one, which is on the 192.168.1. Range. The default gateway IP address, which is configured on the router interface there, connecting to the switch, it is 168.1.254 with a different MAC address, any MAC address on this particular physical interface of the router. Similarly, you have another segment on the right side, but its network subnet range start 192.168.2. It's not 1 as the other one. So it is a different subnetwork, and if you are communicating between these two, you need to have a router in between for the routing function. And some of the router examples available in the market, this is quite old now. These names and numbers are different. And there are something called multi-layer switches. Multi-layer switches having the switch processor and the route processor. The requirement to have these ones is this. Initially, you created you have a network switch, and you created 3 VLANs for 3 different departments. Now, let's say VLAN 1 is for HR, VLAN 2 is for marketing, VLAN 3 is for production. Now, each and every department has its own security domain or own failure domain separated or VLAN created. But suddenly, you have a requirement to communicate between different departments, which means inter-VLAN routing or inter-VLAN routing must be enabled. So the way traditionally it has to be done in by connecting switch with a router by using 3 physical interfaces, 3 physical cables and interfaces, 3 ports required from the router and 3 ports required from the switch end for the communication. That is for the inter-VLAN routing to communicate between different VLANs or different departments. Now it can be then later people optimize because reduce number of ports and cables, decided to because if you are increasing number of VLANs, let's say you created 20 departments, you created 20 VLANs for them. The switch ports are not sufficient to interconnect sometimes if you have 16 port switches. So that's why it is not scalable solution. So people build something called trunk port. So switches and routers can be interconnected by using a trunk port. This trunk port carrying multiple VLAN traffic by the physical port separated by 2 virtual ports. It's a solution called a router on a stick. So you can carry multiple traffic for the inter-VLAN communication by using a single physical link. So now you somewhat optimized by you are using single physical link rather by creating VLAN by using a trunk connecting by trunk port. So it's a kind of optimization, you can see that. But later people realized that rather than having couple of different devices for routing and switching, you can have single device with the routing route processor and the switch processor. That is named as routing is on the layer 3 of OSI model, switching is on the layer 2 of OSI model, which is on Ethernet or MAC address. The routers are based on IP addresses, which is the layer 3 of OSI. So that therefore layer 2 and layer 3 functions are possible with the switch processor. You can proceed with the layer 2 functions. The route processor can be processed with the routing functions on a same device, which we usually call multi-layer switch, layer 2 and 3. And you can communicate between different VLANs by using a multi-layer switch rather than having two different devices for the purpose. So this is a kind of gradual optimization by network designs. So that's the purpose of using multi-layer switches, and there are further optimization of multi-layer switches. For an example, it's not you just need to route only the first communication between two VLAN host. Then thereafter, you can, if you know the MAC addresses of two ports between the VLANs for specific hosts, you can use the layer 2 communication thereafter. So it is a kind of a optimization possible with the multi-layer switches, which is impossible previously. So if you taken the specs of the routers and the multi-layer switches are much faster than routers due to these optimizations. There is a specification, the metric in there, usually the how many packets you can process at a second, which is usually identified as a PPS, packets per second, or million packets per second. If you compare the specifications between the router and a multi-layer switch, multi-layer switches are much faster due to this integration of layer 2 and layer 3 functionality, which is not the case of routers. So that's why you usually required to use, so necessary to use multi-layer switches rather than routers for your local area network. So enterprise networks you are doing locally. For the remote connectivity, routers are fine. But if you are switching between different VLAN, it's better to use multi-layer switches rather than using switches and routers together. Okay, this is another way of representing multi-layer switch. You have two different VLANs, VLAN 20 and VLAN 10 and 20. And you have two different range of IP addresses, 192.168.10 on VLAN 10 and 192.168.20.20 on VLAN 20. So two different interfaces connected with two segments. And you can see that /24 is the subnet mask representation, which means first three octets are reserved for the network address. The last 8 bits are out of 32, last 8 bits are for the host address. The first 24 bits are for the network address representation. So this is just a recap on the network design course, because I need this information or this analogy in terms of continuation of next topics. Okay. Any questions on these slides? Okay. All right, just give me 5 minutes to complete the bump traffic definitions. Then we can go for a break. The bump traffic means broadcast, unknown unicast, and multicast. So these three types of traffic are there in usually they are in your network, and it is usually destined to multiple receivers. The broadcast, if you send a broadcast, is sending to all the host in your broadcast domain or the layer 2 network. An unknown unicast, it's another kind of a traffic. Even it's sending to it will be sending to everybody in terms of the context. Multicast again is another traffic sending to the multiple receivers. So those are the call in the network world, network engineers identified as bump traffic. So this is the definition: broadcast traffic destined to all the hosts in the network. Unknown traffic, unknown unicast traffic whose destination MAC address has not yet been learned. Because I mentioned in your this thing, the broadcast, the switches initially, once you started power on the switch, it doesn't have a MAC address table because it's a kind of a dynamically learning and filling table. So once you power on the switch of your network, even though your hosts are connected, you have empty MAC address table. At that time, it's only sending. So the switch is not aware of which port connected with which MAC address. So it's just say flooding other than the receive port. Those are called as unknown unicast. So that is another way, another kind of broadcast. So that is the unicast traffic whose destination MAC address has not yet been learned is known as unknown unicast. That's having the flooding behavior. It will be flooded other than the received port of the switch. The multicast is the one traffic intended for multiple receivers subscribed to a specific multicast group. So if any user wanted multiple users requesting traffic to be received from a particular multicast group, then it is having the requirement. It is having the requirement to the destination as a multiple receiver, which is a virtual address. So these three traffic usually have the behavior of one to many. Just one source and many receivers or the many destinations. So these need to be addressed carefully. That's what the collectively referred to as bump traffic. These types share the characteristic of having either an unclear destination or multiple receivers. So unknown unicast doesn't have a clear destination because it's decided to flood. And broadcast having multiple receivers, and broadcast and multicast having, at least multicast having multiple receivers. Broadcast or unknown unicast doesn't have idea of the receivers, just flooding is the behavior. Multicast is more control behavior. It's only sending to the intended receivers. If somebody not requested or subscribed to the multicast group, the source doesn't send any message. So it's quite organized. Broadcast is required for the protocols like ARP to map IP addresses with the MAC address. It is quite important. Unknown unicast is a byproduct like building until you build a MAC address table. So then a traditional layer 2 network, such traffic often leads to the broadcast, flooding, wasting the bandwidth, and increasing the load of source device. So these three types of traffics for traditional networks, about 10 or 20 years back, these three traffic, even though it's multicast somewhat optimized, it is difficult to optimize due to the nature of traffic. Usually the older traditional switches, if you receive multicast, it's for the layer 2 switches, it's flooding. Later, it optimized by several control plane protocols that I can explain you later. So modern day network having something beyond the VLAN. There is something called VXLAN because VLAN has a limitation. You can't create more than 1,000 or sometimes 4,000 plus VLANs. But large data centers require more separation of domains, especially let's say you have a service provider network. There are several companies connected there. You need to separate the traffic there. If you are scaling your network, VLAN may not be sufficient based on its own technological limitations, based on its protocol. So modern day data centers now having spine leaf architecture, as we discussed on the spanning tree and versus fat tree. So those the scalability of modern day network with having a large number of VLANs, you need to create something called they introduce network architectures introduce something called VXLAN, which is extended VLAN, you can have many number of VLANs as you wish, which is a failure domain isolation technique. And if if you are configuring these modern day network with a VXLAN, you need to have tunnel endpoints and need to use technologies related to tunneling, which is modern invention. So those tunneling interfaces need to replicate these traffic individually based on its definitions like VXLAN, tunnel endpoints, and there are several. We will be not covering this VXLAN implementation, just need to give you an idea how complex the modern network and how many failure domain isolations are there like VXLAN. And these configurations require are in a difficulty of handling this broadcast, unknown unicast, and multicast. So you need to configure them properly and careful on these three types of traffic, especially on the multi-destined or sending to the multiple receivers. So therefore, efficiency and reliability forwarding, the VXLAN BUM traffic is the primary application scenario for the VXLAN multicast BUM traffic forwarding methods. So there are new methods to forward multicast or this BUM traffic carefully on the modern network. So therefore, it is important to you to understand how the multicast protocols work, how multicast behave. Otherwise, even you can't use it for the unicast properly because you need to separate early adjust the different type of traffic on the modern network configurations and adjust based on the best practices there. All right. Okay. So we can take the break now. Let's meet up after 15 minutes, which is roughly on 10:45, 10:55.